Okay, good morning. And I'm here for second time at NDC. And first time I wasn't totally unprepared that you are not asking questions. So feel free to ask question, it's fine. Okay, I'm Hana. I'm chair of Czech National Body and member of C++ committee. I'm chairing reflection study group there. And also I'm author of compile time regular expression library. I talk about it last time I was here. So, and also I'm staff scientist on Avast, which is AV company. And this talk is about something I did there. Okay. Code examples. They are all C++ 23 with some few things. And it's a slideware. They are not correct. There's probably many errors in it. And don't worry. And also, there is a lot of code I won't be presenting. It's like support code about crypto and whatever, because that would be much bigger. And also, all the code is in namespace Luna. It's like Lightning update. And I'm using Fira code with legiters. Don't be scared. It's nice font. Use it. It's fun. Okay. The problem I'm trying to solve is I need to update an object on millions of clients every few minutes. Every few minutes, I mean like every 3, 4, 5 minutes. How I do that? Okay, Lightning updates. What can you update? It can be executable. It can be a content, database, textures, models. Every application needs an update. Okay. But generally, it's just a state of the application or part of it. The state is immutable because you don't want the state you are updating to be changed by the application itself. It should be immutable. It should be consistent and secure. So no one will give you something which is not yours, but maybe someone will use it as an attack surface for your application. The state is representable as a data structure. Everything is data structure. Vector of byte is data structure. Array is data structure. Tree is data structure. So every data structure can be somehow represented as a file if you serialize it into different format. And it contains your data. It's a subject of the update system. And I'm using term subject a lot during this, in this talk, so this is important. Updating mechanisms in your applications can be replace everything. Every time you update, you just replace everything, and you are done. It can be some overlay over your current data, like this. And also it's fine. Also, it can be differential update, that you are applying patches every time you update. You change what you have with something to something new. Basically, you have state n plus difference between two states, and you will get new state. And difference can be, like, it's just like a cell in a matrix of states. And matrix can be an update graph, like graph, because it's same. So let's say we have state A, and then later we will update to B, and C, D, and E. Makes sense. But what happens if your clients they are not always on the latest version? Sometimes they are on older version because they were on vacation, maybe. So you need to have a shortcut in a graph, like this. And it's obviously easy to find a path in your graph if you look at it. So between A and E, it's really easy to find path because just simple, direct one. What about A and D? You see it. That's simple. Okay, but if you don't see the graph, what do you do? From B, you will look forward in time, but actually you cannot, because B was released in time when you didn't know what we are going to release next. So you cannot do that. But you can go forward, backward, from E back in time. But what happens if there is no direct path from E to B? You need to somehow find a path in the graph. Maybe it's C to B. Basically, the algorithm is easy. You will look for the closest next node to the one you already have. And then you find a direct path, apply the patch in a reverse order, and you are updated. Okay, how do you represent a link in the graph? It can be file name. It can be a file name with a version number or name of the release. Like this is the latest final to like Word documents, obviously. Or identifier of its content. That's much better. You can actually calculate a hash, unique hash of the content, and use it as a name. This will create a unique identifier of a content. So you can say that hash value of the content is a pointer for the content. And unique value for its content it's called content addressable. So if you knew what's going to be there, only its hash, you can actually download the file based on the name from CDN, which is like just a bunch of networks on around the internet, servers on the internet. And also, if you knew the hash, it makes the data immutable. This file will never be changed because the file, if you change it, actually should have new name. Okay, and because it doesn't change, it's really easy to cache because it will never change. So caching problem is suddenly much easier because you don't need to think about invalidation. You will just add it into cache for some time, and if application is asking for it, it's there. And some later you can just delete it and it's fine. And if they ask, you can just load it again. And also, if you store the hash in the graph as part of the object, if you knew hash of A, which contains hash 2 of B, you actually can trust also C because it's contained in B. So it's transitive trust. So let's say we have graph BCE. And it's not just like these states we are updating. They are just actually we need only metadata, like description, what's the data inside the graph. And the links between them are like just identifier of previous metadata. So each metadata contains description of the content you are supposed to be in. And between each metadata node, there are a new node containing the actual patch or diff, if you will, and previous metadata. So you just need to download a patch from previous metadata, and it will give you previous metadata, and also difference between previous subject and your subject. And also some metadata can contain a snapshot, which is just serialized subject. So you don't. Somehow you need to start the graph because subject can be just unpacked snapshot, or subject can be subject plus multiple of patches, and subject can be unpacked snapshot plus multiple patches. So there is a graph, and let's say we want to update into C. But we don't have anything. Our application is clean slate. I just got somehow the C and I want to get full update from it. I will just look on path to closest snapshot, download one diff. By that I got the metadata of previous node, and then I will download another diff. That will give me metadata of another, and then I will download snapshot, deserialize it, get subject and another subject, and I'm done. My application is updated to from nothing. I got current latest state. Okay, and now when you actually kind of understand what's going on with the update system, we can model it. So I will start with the hash because it's a pointer and we are C++, so it's a pointer. So we need to model pointer. And we can say that hash is just array of bytes. Like let's say 32 bytes if it's sh256. And hash view is just span of bytes, immutable. Okay, so I have, but that's not working because I like strong typing. I don't want some random bytes to like be interpreted as a hash. So I need something which is more strong. So I can create my own type hash. I need to write some constructor. There is the array. I need to implement some comparison. We can default it. Some iterators, non-constant iterators. Then I need to do much more. Then hash view, it's same. Constructors, comparison, we need to implement our own because span is not comparable. Also iterators, but it's a lot of code you need to write for just something so simple as a hash. So I don't like it. I like strong typing with via inheritance. I have type hash, which is inheriting from stat array, which will give me everything I need. Comparison, iterators. And I just need to create a constructor, which will just from hash view create new hash. It's explicit. And also I need to take the constructor of array and explicitly all the constructor raise to same level of priority, let's say, as my own constructor. Nothing else needs to be written. That's the best code, the code you don't need to write. And hash view is same. It's a span. I will take its constructor, create an implicit constructor from hash because it's a view, and my comparison. And that's all I need to implement. It's just few lines of code. You don't need to you need to test only few functions, and everything else is already there. And then I can create also hierarchy of types. I can create a tagged hash, which takes tag. Do the same, create a new constructor for the tagged view. Tagged hash view, it's just exactly the same, just another layer. And then I can introduce tags for my sh1 function, sh256 function. And now I can create a sh1 view, sh256 view, and they won't mix because they are different types. So you can have a function. Yes, Björn? You won't find any like comparison operator because yeah, actually like maybe yes. I will get to back because there is like I have something more about it. So we have the types, and now you can see the graph. What is a convertible array which owns data is convertible into span implicitly. Hash value is convertible in hash view, and also hash value is convertible in span. And this is just implicit conversions. Take value same. So you can actually take your, if you want, take bytes from your text hash and place it into function which expects span of bytes. It will work, but not otherwise, because otherwise you need explicit conversions. So downcast is okay, upcast must be explicit. Okay, as Tony said, strong types create strong code, because if you create strong types in your application will be much safer than if you can mix arguments or types. So do that. Oh, sec. When we introduce the type hash, now we need to introduce type metadata, like one denote describing our state. And metadata contains hash of the subject, the data we are updating to. So when we finish the update, we can actually check if we are in correct state. Also, it contains color of the graph to distinguish between multiple graphs, if you have multiple branches or A/B testing, whatever. And also, each node has a timestamp when it was created, because I need them sorted. It's actually ordered because you cannot go back in time. You need to go only forward. And then there is a list of links to previous metadata. I call them delta links. And they are like actually linked to a div or patch. And also some of the metadata can contain hash of the snapshot. So you can download it and unpack it and get the subject itself immediately. And there's like two member variables which are not serialized later, but you need to know them for the algorithms. The hash of the metadata itself. So when you serialize it and calculate the content, then that's the and calculate the hash. Is this the hash? And also, if you have the serialized bytes available, you need them later in algorithms too. So when you download the file, download the metadata, and unserialize them, you need to store their identifier and their content in the object itself. But these two are not serialized. Maybe in future there will be like maybe attribute to mark them that these won't be part of the serialization process, but for now it's just like this. And delta link is a timestamp of the previous metadata and hash of the delta object which leads to previous metadata, and also distance to closest snapshot, because this snapshot is not in each metadata node, but only in few. Maybe let's say once a week you will release a snapshot. So you need to this distance is needed to find the closest the shortest path to find it. And there is also comparison operators which can be defaulted, because actually I only thing I need is to order them based on the time point. So we'll get there. Delta is much simpler object. It's just metadata of previous state, because they are contained there, and bytes of the patch itself. I don't need to understand it, but it's just some sort of patch. And snapshot is just bytes of the content of the serialized content. And actually, I'm not using inheritance here because actually I don't need them access for all the functions like iterators, because no, that's just like something inside, and don't get cozy. And then I need actual identifier, which is really helpful because I have multiple types of object. So I have identifier of some tag, and which contains hash of the object I'm pointing at, and type. And I can compare the identifier against the type, and also I can kind of serialize the identifier into URL by giving a prefix. So if you have your server or CDN where all the objects serialized are stored, you can just use it as a prefix, operator divide, an identifier, and it will give you nice URL to download. You can provide to some library which will download it for you. So we have types: metadata, snapshot, delta, and we have alias. Alias is something special. It's actually metadata, but they are not stored on CDN under its hash, but under its name. Let's say we have a graph, and as we are releasing in time, we mark this node C as a beta release, and node B is stable. So users can change if they are in like beta stream or stable stream. And then when we decide that our beta is stable enough, we just mark it as a beta. And we can do that because we actually storing the aliases as under name of the alias, not under name of the hash of the content. So we can actually change them. And I'm using different identifiers, that's like different suffix, to actually change different CDN caching rules. So we have alias, it's just a copy of metadata stored under name, or it can be also hash of the name, which has nice property because you can actually seed all hashes in your graph with identifier of your stream. So you can actually have multiple like components updated from same URL, and they won't conflict. There will be no conflict between them. And because you have the file extension different based on the type, you can actually mark your server or CDN to cache it differently. Like, let's say for alias, it's great only to cache it only for 5 minutes, but for everything else, indefinitely. So how you deserialize bytes into object? I don't know, it's like use your own favorite library. But before that, I need something I called any object, which is just variant, because you can inherit from variant. And take its constructor, so it will work nicely. And then I have a function get metadata, which will give me metadata if there are any, as a pointer. And because I don't want to use write const function and non-const function, I can deduce this, explicit this argument, which is C++23 feature. It's cute. And same thing for delta, same thing for snapshot. And then I have a wrapper. I'm using protobuf. How many of you use protobuf? Okay, few hands. JSON, XML, YAML. Oh, okay. So I have object type, metadata, patch, snapshot, and signature. Signature will contain a cryptographic signature of the hash of the content. We'll get there. So you can actually have like some security in your update system. Anyway, first function I need to do is unwrap and validate. I will take identifier of object I just downloaded somehow, and its content as a byte, just view to bytes, and I will return any object which is a variant. It can be metadata, snapshot, bytes, whatever. And I deserialize it with protobuf. Some library, there's plenty of them. Probably maybe you write your own. It's a sin, but everyone is doing it. Then if in the wrapper we know that the type is metadata, and actually it contains metadata and signature, because every metadata needs to have a signature, we call function validate metadata with its ID, metadata content, signature, and content of whole object we just downloaded, because we need it for later. And then if it's delta, delta needs to contain metadata of previous state and also the patch. And then we'll call function validate for ID, metadata of previous and patch. And if it's snapshot, it needs to contain snapshot, and we call function validate. Otherwise, we throw exception it's not valid object. So validate metadata looks like it's quite simple function. It will take identifier, content of the metadata, signature, and content of the whole wrapper, and return metadata. So if ID we ask for is not metadata or alias, we ask for different object, and it's like precondition error, but we will throw error because this is like code which is interacting with something getting from external, so you need to check everything to be secure. And then I calculate hash of the content, not the wrapper content, but the content of metadata only. And if the ID is metadata, because alias doesn't need to be identified by hash, we compare if the hash is same as the hash we ask for. If it's not, we throw an exception. And then we can validate a signature for metadata, even for alias, with some trusted keys and a hash and signature we just got. And if it's invalid, we just throw exception. This is the code. I'm not going to show you because it's just like, it's not trivial, but it's not scope of this talk. And then I deserialize the content of metadata itself because it's protobuf in protobuf. And then into result, I store the hash I calculated, and I copy the bytes of the wrapper because I have only view with strategies2. You can do that into vector of bytes and return result whole object as the result. Yeah. And delta looks similarly. You take identifier, metadata bytes, and patch bytes, and return delta. If you didn't ask for delta, obviously it's an error. Then you calculate a hash of metadata bytes concatenated with patch bytes, because you need to trust both of them. And if the hash doesn't match with what you ask for, it's an error. And then you ask for deserialization at metadata and calculate hash of the metadata. These are not signed, but don't worry, you don't need it. And then you will return delta with metadata and again copy of the patch from the view. And you got delta. Snapshot is the simplest one. You ask for identifier and some data, you will get snapshot. If it doesn't match, it's an error. You will calculate the hash. If hash doesn't match, it's an error. Then you will copy the data and return snapshot. And you are fine. So we have the verbs of our algorithms. We have hash, identifier, metadata, snapshot, delta, alias. And then we need to have some like, nonce. Verbs, we will get verbs, sorry. So we have the graph. We have some object in it, and let's say we want to go into state C. Yeah, and there is like the graph, which is stored as a file. And our application is in state C, which somehow points at the state C. And the pointer is actually a shared pointer, but we will get there. So we actually own in application the state and the subject. And every time we update, we just create a new one and release previous one, and new one and previous one is released. Okay, so state of the application is constant metadata. We don't need to change them. And our subject, which is also constant, because we are not going to change, it's immutable. And also some function for the hash, color, and timestamp. But actually, it cannot be just our object, because in update system, you're actually updating quite a lot, quite a big object, like let's say a few hundred megabytes. So you don't want to copy every time you copy the object. It's better to have shared pointer of const t. How many of you think that shared pointer is a terrible thing to use? I know Bjorn, but he already saw this talk, so I don't know why he's like raising a hand. Shared pointer of t is bad. Shared pointer of const t is actually awesome thing, because it cannot form a cycle of dependencies. So it will never leak. So if you have big object and you know it will never be changed, it's a resource, just use shared pointer, you will be fine. And also, as it behaves as immutable value, you don't need to for locking when you access it, because you can just read it. It's const correct, and also it's safe memory because you don't need to create copies. So if you are in like embedded development or anywhere, it's a resource, and if you don't know if you like where you need to hold it, shared pointer can help you, and it's fine. So let's have another update graph. We are in state B as the application, and we want to go into state G. How do we get there? We download the metadata of state G, and by downloading them, we will get links to some previous states. How do I select which I should download next? Pick by random? Yeah, I can do that, but it's not effective enough. Actually, the most effective way is to look for the node which has lowest timestamp greater or equal as my current node. Because the graph itself has like one requirement that there is always path -1. So you can always go back. So I will download E and will get C and D because the nodes are actually on the in the graph sorted by time. Obviously, I will download C, and from C I will get delta to B. I will download it, and I have path from B, C, E, G. But the graph actually is much more complex. But I don't need to see it. I just need to see what is in my current node I'm downloading. So let's implement it. So we have function select next, which takes metadata and some current state, which is also shared pointer. And it returns identifier of object I need to download next. First thing, if I'm not in a current state or color of the graph is different, so maybe I switch branch between totally unrelated graphs, I mark it that current state is empty, and I will do full update. And if I don't have current state, so I'm doing full update, and timestamp of the node actually I'm supposed currently in, and current state is older, then I mark it as also full update, because the metadata I just download are, sorry, I'm just getting lost. Yeah, if I'm asked to download update which is older than I'm currently in, then I need to do full update, because there is this algorithm doesn't support going forward. It is going only always backward. And also, all graphs needs to contain snapshot hash or at least one delta link. Otherwise, the graph is wrong. So, if we are doing full update and there are no delta links, and there is a snapshot hash, we just tell the callee that you just need to download a snapshot of this hash, and it will be fine. But if we do have current state, we need to select the best link to go. So we will look at them, filter them, pipe them into filter, and filter them by eligibility, which is just the link timestamp must be bigger or higher than my current state I'm updating from. And then when we get only the filter one, we look for the lowest value, which is the closest to our node, and select it. And build identifier from it of type delta. So this is your delta you need to download. But if we are doing snapshot update, but there is no snapshot, like full update, we look also into delta links. We also look for the lowest value, but we are looking at the distance to snapshot. This is called projection. And with this, we will get the lowest timestamp of delta link, shortest path to delta link, because this is just like maybe number of bytes you need to download, or number of jumps, whatever you optimize for. And then we will take hash and create a delta identifier and tell our user to download delta from this delta link. Okay, so you can actually represent path through graph as a vector of any object. And then you need function which will takes identifier of your update target and give you path you need to go to find path from the object you are going update to into a state you are updating from. So, and now you need to do it asynchronously because you are actually talking about downloading something from internet or from storage at least. So let's start. Like I have function convert to object, which take identifier and function which asynchronously download bytes. You provide it because that's not like that shouldn't be delivered by a library. That should be delivered by your application because your application on your platform needs your own function to interact with I/O. And identifier the function, and it will return task, which will return any object. And this will only like ask for downloading the object with co-await. Then it will unwrap it and return a result. Everything is asynchronous. Async fetch function needs to like be invocable, return. If you call it with identifier, it needs to return available for something. This is not part of current standard library, but there is multiple libraries you can use, like CPP Coro or what others. Anyway, and it will give you a return. So you will fetch bytes based on the identifier, co-await. So this coroutine will pause until it's downloaded. And when it's downloaded, it will be resumed, it will be unwrapped, and it will return the unwrapped object. From bytes, you will get the deserialized object and validate it. Otherwise, there can be exception also. And your download function can be just calling curl or calling fetch on iOS or whatever. So fetch path is a function which will take current state you are in, which is like we are updating from, hash or name of the target. It can be hash of the state or it can be name of the alias. And it will give it function which will download bytes for you, nothing else. And it will give you path you are updating. So the result path is just vector of object. Then there is a function which will is returning task, but it's not coroutine. It's just doing wrapping. It creates a lambda. If you ask for identifier, it will give you object by using your function to download and an identifier. It's just like small wrapper. So take blob, download it, and so on. And then if you're asking to download it to latest hash you are already in, nothing needs to be happen because you're already in. So it will return empty path because path from here to here is empty. But if not, then you need to convert the identifier of the target. If it's alias, it will convert into hash of the name. If it's hash of the state, it will convert into hash of the metadata. Then download the object, wait until it's finished, and then you place the object into path as the first step. And then you will repeat, and always look at the last piece, like last part of the path. And if it's a metadata, then and you have current state and metadata hash are same, you are finished because you already found path to your state. But if not, you need to select next with function I showed you before from current metadata and current state. It will download the object, co-await on it, and place back into vector, and repeat. But if you got delta, you will place previous metadata from the delta itself on the path. You don't need to download anything because you already have the metadata as part of the delta. And continue. If you get snapshot is always end of the path because that's all you need for the update. Then you return path. That's all. You finish your you're iterating through it, and you found the path from the target you are supposed to update to, from the target you are updating from, and you are doing backward in time until you find the path. So path from NM is just state n plus path from MM, and it's just delta, delta, delta metadata, and you are finished. But in reverse. Anyway, so we have application which is in some state, which is some subject. If we download, we got path, and we need to apply it in reverse order to get another state, and we applying delta, we will get new subject, and we can apply another delta, we will get another subject. And when we are finished, the state is current state of the application. The update state function just takes the atomic shared pointer to current state because you want to be able to switch it atomically. Target of the update, and fetch function which will download bytes for you, as I show you. And it will return update results, which is like information if update was successful or not. So you will load the atomic pointer of current state, so you will get copy of the share pointer. Then you will fetch the path, the function we did, wait until it's finished, and then when you are finished, you pipe it and fold it from right, which is like state accumulate, but from right, not from left, and apply, which is new type, apply update traits, which is something which is describing how to apply patch, and that's how you will get new state. Then, if old state is not null pointer, so we can check, and new state is actually same as the old state. We just tell user that we already we are already on the latest version. Actually, nothing happened. Maybe I got empty path. But actually, I didn't create any copy because everything is just shared pointer, so I didn't create any copy. So it's fine. Otherwise, I will atomically store the new state and propagate. I actually update you to latest version, and you can react on that. Maybe store the object into persistent storage, maybe, and apply functor. Let's say it's just some template for update traits. Update traits is a trait of your type you are updating, because this update system can work with any data structure you want. It can be vector of bytes, it can be tree, whatever. You just need to describe how you update it. And if you get snapshot, I can actually ignore the previous state. You will get new state. And it's just easy because you just deserialize the snapshot by your provider function, because I don't know how you serialize your snapshot. And take empty metadata and return state you are in. This is your new state. If you get delta, you need to have previous state. So you apply from traits, apply patch function to your subject with your delta patch, and create new state with make shared, return it. Again with empty metadata, because all paths, because when you download it, first time you always download metadata object. So all path, if you apply it in reverse order, will end with metadata. So you can actually check if you are in the latest state. So at the end of the path, there will be always metadata you can check against, which means you can calculate hash of your subject, and it needs to be equal to what you are expecting. If not, it's exception, it's error. Otherwise, there is a new state which is sharing the subject with previous one, but the metadata are checked, and I can provide it to you, and that's all. Okay. And update trace look like this. It's just some example. You need to somehow calculate hash for consistency. You need and return some hash. You need to calculate difference between two states. When you are building the graph, you actually share the code in producer and in consumer, which is awesome. And return just blob of byte. And you need to be able to apply the difference. So you will take the subject and apply the difference from the previous function, and you will get new subject. And you also should be able to serialize it and deserialize it, so it can be stored. Okay. And user-facing API, how you use it? Again, we have application which is in some state and owns some subject. I start updating asynchronously, maybe in different thread, and it starts updating. So meanwhile, I will get subject too. But suddenly user do something, and the something, some process, needs the data I'm updating. But I'm still in process, so the user will get reference to subject, the old one. And meanwhile, I can do update, but when I will switch them, I will get a dangling reference. That's the reason I'm using shared pointer. So it will never happen. As long as you are holding the shared pointer inside your process, which is using the data, it will never dangle. So when your task is finished, there can be another task which can start with the latest data. Meanwhile, you can cancel the old one if you want, but it will never dangle. So I call it stream because it's like stream data. And it's just class which contains atomic shared pointer of the state, which is owning the type I'm updating. The function update to I showed you before. Then there is a function get, which will give you shared pointer of the subject itself. If there is any, if there is none, it will give you null pointer, obviously. And also you can ask it to serialize current state. So user can ask the component to serialize it so it can be stored on persistent storage for if you want to do restart or whatever. And serialized state function is just takes the current some state. If it's empty, it's exception. It must own the original data of metadata, so it must be valid state. But it will always be a valid state. And then you just concatenate somehow the metadata and the subject itself, call the traits to serialize it, and you are done. The serialization is similar. You will get input. If it's empty, the resulting state will be null pointer. Then you somehow split it, create a path. You will, from the split, from the content, you will create a new snapshot, just like ad hoc snapshot there. And you will unwrap the metadata because they are exactly the same as you download them. Create the valid object. So you get path, and then you fold it from the left to right, exactly the same as we are doing update, against empty state. And with current update traits, and you will get the latest state you are in, and your application will actually validate it for you. So if someone will tamper with the data stored on disk, you will detect it. And it's using exactly the same code as the updating mechanism. Then there is always a stream constructor, which is just default. And there is a constructor which will take optional of span bytes. If you provide it, it will deserialize them and create a run-in state you are supposed to be in. It's optional because you can provide null opt if maybe your function give me the latest store data. Won't download anything. It will return just null opt because it's correct state. It's not exception, so you can just like pass it through. Okay, and how you use it? You have like you are in main. You have this stream, and in this case, I'm updating map of string to strings with some traits to update them. It's like some sort of database, maybe config database, and I have a function which will download, which will load file config bin and provide it to me at the start. Then I have a coroutine which will do the update for me to the latest alias or tag if you want. And if actually I did update during the update and I'm not on the latest version, I just store the file. So next time I run the application, it will be on the latest version. So at the start, I will initialize asynchronous update. I can wait for it. And also with some scheduler, I can plan the update to be checked every 10 minutes, maybe every 5 minutes. And then whenever I do something with the, I want to do something with the subject I'm updating, I just need to get a handler, shared pointer of it, and hold it as long as I need it and access it as a reference. And then I do the work. So, but the essential part for your application is actually the stream of some object, in this case, vector of bytes, and trace maybe by sdiff, and getting the handle. Everything else is not specific for your object. So it can be a one-time code for downloading, one-time code for storing persistent files, and nothing else. It's only these two lines of code you need to use in your code in order to update it. Yeah. BSDiff is just like the library, so it's just wrapper. So it calculates the hash of the subject. It calculates the difference of the two states, apply the difference, serialize, deserialize by just copying it, and that's all. So I told you at the beginning, I need to update an object, whatever object, on tens of millions of clients every few minutes. Actually, kind of lied to you. I showed you only part of it, because everything can be done on client, which is much cheaper. And now the problem is actually, I just need to deliver hash value, 32 bytes, which is just graph head, to tens of millions of clients, which is much simple task to do actually. So I showed you today how you can model algorithm into code. You have verb, nouns. It's if you use strong types, it's easy to reason about what you are doing, and you cannot actually usually do the wrong way because it won't allow you. Also, C++ can be fun. I'm not saying it lately on my Twitter because I start learning JavaScript, but yeah. And use cases, you can, as I'm doing, distribute AV signatures to our clients every few minutes. But you can also use it in smaller scale to synchronize configuration across the cluster of servers. Or you can distribute machine learning models to your application so it are run on clients privately. You can actually update anything. Everything is a data structure, and more. And some of you maybe guessed that, but let's say we have map of path and bytes, and this we need to create update traits for such a virtual file system, which is just calculating hash of the file system is a hash of all names and contents, and then hash of the all hashes. their difference is just like iterating over all addition, removal, and changes, and creating a patch of it, and somehow serialize it, whatever, that's not important, and compressing it. Applying difference is just deserializing the patch and creating a copy of current virtual file system. I strongly recommend to use copy on write data structure. And applying the difference by addition, by just inserting into map. The removal is just erasure from the map. Change is just, I will take key, look for it, and change the content of the value. And yeah, and serialization is just, I will serialize the whole data structure and compress it. Deserialization is exactly opposite. And that's how you will make your own simple gate. Thank you. Okay, we have a bit of time, so if you have any question, if you are afraid to ask publicly, you can approach me. It's fine. And otherwise, thank you.